Gravitational waves are among the most fascinating discoveries of modern physics, a concept that connects Einstein's century-old predictions with some of the most violent events in the universe. To understand them, imagine space-time, the very fabric of the universe, as a vast, flexible sheet. Just as a stone dropped into water creates ripples, massive cosmic events such as colliding black holes or exploding stars send disturbances through this fabric. These disturbances spread outward at the speed of light, carrying information about their origins across billions of light years. Those ripples are what scientists call gravitational waves. The story of gravitational waves begins with Albert Einstein. In 1916, while developing his theory of general relativity, he proposed that accelerating massive objects would produce ripples in the geometry of space-time itself. Yet even as he described them, Einstein doubted whether humanity would ever be able to detect such faint signals. Gravitational waves stretch and squeeze space as they pass, but the effect is unimaginably tiny, comparable to changing the distance between Earth and the nearest star by the width of a human hair. For nearly a century, the idea remained a theoretical marvel, unconfirmed but deeply embedded in physics. Everything changed in September 2015, when the Laser Interferometer Gravitational Wave Observatory, LIGO, made history. After decades of engineering challenges and scientific persistence, the twin detectors in Louisiana and Washington captured the faint signal of two black holes spiraling together and merging more than 1 billion light-years away. The signal, a tiny oscillation in the fabric of space-time, lasted less than a second but confirmed Einstein's prediction with stunning clarity. It was not only the first direct detection of gravitational waves, but also the first direct evidence of black hole mergers. Announced in 2016, the discovery earned the 2017 Nobel Prize in Physics and opened an entirely new way of exploring the cosmos. Unlike light or radio waves, which can be blocked or scattered by matter, gravitational waves pass through everything virtually unimpeded. This means they carry pristine information about events hidden from telescopes, like black hole collisions, neutron-star mergers, and perhaps even clues from the earliest moments after the Big Bang. With instruments like LIGO and its European counterpart Virgo, scientists can now listen to the universe in gravitational waves, much like adding a new sense alongside vision. The cosmic symphony they reveal tells us stories we could never have uncovered with light alone. Today, gravitational wave astronomy is still in its infancy, but it holds extraordinary promise. Already, we've learned about the population of black holes and neutron stars in ways once thought impossible. Future detectors, like the space-based LISA mission, will allow us to explore even lower frequency waves, probing supermassive black holes at the hearts of galaxies. Each detection is more than a scientific achievement. It is a whisper from the universe's most hidden corners, reminding us that space and time are not silent, but alive with motion and memory. Gravitational waves, once only an idea, are now a gateway to a deeper understanding of the cosmos.